Hello everybody, welcome into another lesson. So today we are starting the unit on applying trigonometry. And in today's lesson, this may sound a little familiar from Algebra 2 Trig for those of you that took it with me or if you had previous exposure in other courses. But what we're going to talk about today is called the law of sines. This will enable us to solve for oblique triangles. And simply put, an oblique triangle is a triangle that's not a right triangle. So it could be an acute triangle or an obtuse triangle. Those are oblique triangles. Basically any triangle that doesn't have a right angle is an oblique triangle. So the law of sines gives you some proportions. It gives you side A to the sine of A equals side B over the sine of B equal to side C over the sine of C. Now you're not going to be using all three of these at once. You'll use two at a time, but this is just setting up the proportions for you to aid you in what to do. Now, the law of sines applies to angle-side-angle triangles, angle-angle-side triangles, or side-side-angle triangles. If you wanted to try to use this to solve a side-side-side triangle or a side-angle-side triangle, it would not work. For those last two cases I mentioned, for either side-angle-side or for side-side-side, you would need what's called the law of cosines, which we will talk about in a couple of lessons from now. But if you have an angle-side-angle or angle-angle-side triangle, there's only one possible triangle you could have that would fit the criteria of the triangle you're trying to solve for. Now, the side-side-angle triangle, where you know two sides and one angle, the other ones you know one side and two angles. The side-side angle, you know two sides but only one angle. This is what's called the ambiguous case. You could still just have one possible triangle, but it's possible you could have two possible triangles that work for the triangle you're trying to solve for. It's also possible you have no triangle that exists. So these are probably the most interesting. Now you can use the law of sines on right triangles, but you're probably doing more work than you need to, because for right triangles, most of the time you could just use the basic geometry or basic trig to solve for the missing angles. So let's get into some examples here. Let's see, I want to do here, let's set up our triangle. Now, where a lot of people go wrong, this may look like a right triangle, but it's not. A lot of people go wrong in the fact that they don't arrange the triangle properly. So they can label their angles correctly. Where they make the mistake is then they take this as side A, this is side B, or this is side C. That's not how that works. The sides you want to label, so the side opposite angle A would be side A. The side opposite angle B would be side B. The side opposite angle C would be side C. You want to label your sides properly, because otherwise you're going to get skewed and wrong answers. So let's see, they give us in this case that angle A is 25 degrees. They give us that angle B is 60 degrees. Then they give us that side A has a length of 12 inches. So we know an angle, angle, and a side. So this is an angle, angle, side triangle, which means that there's only one possible triangle that meets this criteria. So we want to solve for all the missing pieces of the triangle. Definitely the missing angle and the two missing sides. What I would definitely suggest is, first thing, find your missing angle. So to find angle B, the measure of angle B, of course, would equal 180 degrees minus 60 degrees minus another 25 degrees, which when you do that should give you that B is equal to 95 degrees. So we just found the measure of angle B to end up being 95 degrees. Okay, now let's solve for some missing sides. We know side A, but what about side B? Well, you want to relate your sine ratios using the law of sines to a side you know. We know side A is 12 inches, right? So you could take that 12 inches over the sine of A, which is 25 degrees. Now, we want to find side B, so that means we're going to set this equal to side B over the sine of that angle B we just found, which is the sine of 95 degrees. So this is how you use the law of sines to set up your proportions to solve for missing sides. Now we just cross multiply. You would end up getting that B sine of 25 degrees is equal to 12 inches times the sine of 95 degrees. So then B would be exactly equal to 12 inches times the sine of 95 degrees all over the sine of 25 degrees. Which then means we can get a decimal approximation for B. I think we'll go to 2 decimal places. I think that sounds pretty good to me. So let's go ahead and do that here. Let me just break out my calculator, make sure it's in degree mode. We're only going to be using degrees for today's exercise. So 12 times the sine of 95 degrees, take that, divide by the sine of 25 degrees, you should get a length of about 28.29 inches. So to 2 decimal places, side B has a length of approximately 28.29 inches. Now we can do the same for side C. As for me, I'm going to choose to relate sides A and C because I rounded B, and that might give us a slightly skewed answer, where at least for side A we have an exact value. So to find side C, let's take length of A, which is 12 inches, over that sine of angle A. Well, that's going to be the sine of 25 degrees. Set that equal to your side C, which you don't know yet, but angle C is 60 degrees, so this would be C over the sine of 60 degrees. So that means then we'll cross multiply, so take C times the sine of 25 degrees. That would equal 12 inches times the sine of 60 degrees. So then C is exactly equal to 12 inches times the sine of 60 degrees all over the sine of 25 degrees. So then C, we should be able to get a 2 decimal place approximation. So let's go ahead and multiply all this. So 12 times the sine of 60. Now take that and divide that by the sine of 25 to 2 decimal places. You get that C is approximately equal to 24.59 inches. And we have just found all the missing pieces of the triangle. So you solve for B, it's exactly 95 degrees. And then using the law of sines, you get that side B is approximately equal to 28.29 inches. And then you get that side C is approximately equal to 24.59 inches. Alright. Well, that's the first one. I want to do at least one more angle side. And then we'll do a couple angle side angles. And then we'll go on to the ambiguous case, which can be a lot of fun. So we're definitely going to stick with an angle side for the next triangle also. Let's just label this all correctly. Okay, what do we got? Another one like it. So angle A is 35 degrees. Angle B is 55 degrees. And then side A is 18 millimeters. Alright, so we know angle A, we know angle B, we don't know C yet. But then we know side A is 18 millimeters. So we have an angle, and a side. This is another angle, side case. So it's probably best we solve for that missing angle C. So that means the measure of angle C is going to equal 180 degrees minus 35 degrees minus 55 degrees. Alright, so what is, let's see. That means the measure of angle C equals 90 degrees. And I do apologize that this is not exactly to scale. But I don't want to have to keep redrawing the triangle. So C equals 90 degrees, okay. And again, I know it's not to scale, just bear with me. So now that we know angle C, we've solved for all the angles. Now we need to find the sides. Well, okay, we know side A. Let's go in alphabetical order and solve for side B. So let's take, of course, let's relate this to side A since we know the length of the side. So this would be that 18 millimeters for side A all over the sine of 35 degrees equals that side B over the sine of 55 degrees. So then that means we cross multiply. B times the sine of 35 degrees should equal 18 millimeters times the sine of 55 degrees. So then, let's see, B would equal exactly 18 millimeters times the sine of 55 degrees. All that divided by the sine of 35 degrees. And now we should be able to get a 2 decimal place approximation for all this. So let's go ahead and solve this. And then let's divide that by the sine of 35. Okay. So to 2 decimal places, you get that side B is approximately equal to 25.71 millimeters. So once you input all that, you get that side B is approximately equal to 25.71 millimeters. And then of course, let's go for side C. Well, since we for sure know the exact length of side A, we should also probably relate side C to side A. So we could take that A length of 18 millimeters, divide that by the sine of 35 degrees. So we're trying to find side C, so set that equal to C all over the sine of 90 degrees. Well, then that means that C times the sine of 35 degrees equals 18 millimeters times the sine of 90 degrees. Well, this is easy. What's the sine of 90? That's just 1, right? So you would just have 18 millimeters over here. So C would equal 18 millimeters divided by the sine of 35 degrees, because the sine of 90 is exactly equal to 1. So now we should be able to get a 2 decimal place approximation. So take 18, divide that by the sine of 35 degrees. To 2 decimal places, you get that side C is approximately equal to 31.38 millimeters. So side C is approximately equal to 31.38 millimeters. Alright, now I would like to do 2 angle side angle triangles. And then after that, we'll get into the side-side angle, which can get a little crazy at times. Alright, let me just put this up here so I can remind myself what I'm doing. And an angle side angle triangle will also only yield 1 possible triangle. So the first 2 cases are pretty easy. All right. Let's see if this works when I draw it out. 102.4 degrees. That's 102.4. Angle C is going to be... Now that'd be another angle side. I don't want to do that. I specifically want an angle side angle. AC angle side. Nope, that's not going to work. Tell you what, let's make something up here. So angle A will be 110 degrees. Side B will have a length of 30 feet. Angle C will have a measure of 40 degrees. Okay. So we actually have an angle side angle triangle. So we do know side B, but we don't know angle B. But we know angles A and C. Well, we can easily find the measure of angle B. That's simply going to be 180 degrees minus 110 degrees minus that 40 degrees, which should end up giving you 30 degrees. So that means that angle B itself would be 30 degrees. Okay. Well, we know side B, so if we want to find sides A and C, we should probably relate that to side B since we have an exact length. So let's find side A. So we can take that A over the sine of 110 degrees, set that equal to side B, which in this case was 30 feet, divided by angle B, which would be the sine of 30 degrees. So that means then that A times the sine of 30 degrees equals 30 feet times the sine of 110 degrees. So then that means A is exactly equal to 30 feet times the sine of 110 degrees all over the sine of 30 degrees. Now we should be able to get a 2 decimal place approximation for side A. So let's see, that was 30 times the sine of 110. Take that, divide that by the sine of 30. So to 2 decimal places, you should get a length of approximately 56.38 feet. So that means then to 2 decimal places, side A should be approximately 56.38 feet. Alright, now we know A and B, we just don't know C. But since we have an exact length for side B, let's relate side C to that also. So we could take that 30 feet for side B all over the sine of angle B, which was the sine of 30 degrees. Set that equal to your side C, which we don't know yet, over the sine of that 40 degrees. So that means then C times the sine of 30 degrees would equal 30 feet times the sine of 40 degrees. So then C would be exactly equal to 30 feet times the sine of 40 degrees all over the sine of 30 degrees. And now we should be able to get a 2 decimal place approximation. So take 30 times the sine of 40. Then let's divide that by the sine of 30, which would actually be divided by a half. To 2 decimal places, you should get a length of approximately 38.57 feet. So that should give you that side C has a length of approximately 38.57 feet. And as you can see, angle side angle's pretty dang similar to angle side. It's just a little bit different in as far as which order the sides and angles go, but it works very similarly. I don't think we need to do another angle side angle. Let's go on to side angle, where it gets a little more interesting. That's probably really more what you came for today. First 2 are easy. And it's not that these are necessarily hard, the side angle, it's just well, if you have two triangles, it can get to be really fun. And this is going to be the bulk of today's lesson, actually, is the side-side angle. So we are for sure doing side-side angle triangles now. The only question is, how many triangles are we going to have? So we got that angle A is 58 degrees. We're definitely given that. Well, that's side B. There we go. All right, A has a length of 4.5. It's just 4.5. They don't give a unit. Side B has a length of 12.5. All right, so as you see, we know the lengths of two sides. We know only one angle. We don't know the other two angles, and we don't know side C. So what the heck are we going to do? Okay. Let's pick any other angle. Personally, I'm going to vote we go for B. The reason is because we know side B, which actually you should do that because you know both angles A and side A. You know side B, but you don't know angle B. So let's solve for angle B. So we can take that 4.5 divided by the sine of 58 degrees, set that equal to your side B, which you do know, 12.5, divide that by the sine of B. So we're actually going to solve for an angle, okay? So this would mean 4.5 times the sine of B is going to end up equaling 12.5 times the sine of 58 degrees. So then I'm sorry, that's not what I wanted. That means that the sine of B is equal to 12.5 sine of 58 degrees divided by 4.5. Now, of course, I think it's obvious we want to take the inverse sine of all this. So we can get a 2 decimal place approximation for angle B. So let's go ahead and do that. So 12.5 times the sine of 58, divide that by 4.5, well, 12.5 times the sine of 58 degrees Well, here's the problem. Here's the problem. There's actually no answer. You know why that is? Because this is approximately equal to 2.36. That's the value of this. If you go to take the inverse sine of 2.36, well, what happens? What's the domain of the inverse sine function? It's from -1 to +1. This is well above +1. So this actually doesn't work. So having set this up right away, we don't have to go any further. There's actually no possible triangle for this. We have no possible triangle. There is no path forward with this. And we certainly can't solve for side C or angle C because we don't know angle B. So there is no path forward with this one. So that's a good example of sometimes right out the gate you'll have no possible triangle. So that one worked out actually very nicely. Alright, sticking with a side-side angle. Now, what if we had somewhat similar? Angle A is 58 degrees. They even give you that, let's see, side A is 11.4 this time. But side B has the same length of 12.8. So the length changed on side B. Well, we definitely have a side-side and a non-included angle, so the side-side angle case applies. Now the question is 1 triangle, 2 triangles, or no triangle. So let's see. We know both angle A and side A. We only know side B, so that means we should first seek angle B. So we can take that 11.4 for the length of side A, divide that by the sine of angle A, which is 58 degrees, set that equal to then that length of 12.8 for B all over the sine of B. So that means 11.4 times the sine of B is equal to 12.8 times the sine of 58 degrees. So now that means that the sine of angle B itself should equal 12.8 times the sine of 58 degrees all over that 11.4. Let's see if we get something this time. So let's take the inverse sine of all that, see what we get. Times the sine of 58. Divide that by 11.4. This will definitely work. We get approximately 0.95, so we know that's in the domain. For an angle, so you get approximately 72.21 degrees for angle B. So we do know there's at least one triangle. So we did get a degree measure. Now, here's the other question. Is there a second triangle? Well, first take the angle you have, that's 72.21 plus 58. That's definitely not going to put you over, that definitely will not put you over the 180. You won't even be close to 180. So we know angle B works, because sometimes what happens is you can get an angle measure and still have no triangle, because when you add the other angle, it doesn't work. You end up exceeding 180. Now, we know this works, but what about a second angle? When you take the inverse sine, what is true? You get a first quadrant angle, right? Because that's in the range of the inverse sine function. Well, isn't it also true that the sine is positive in the second quadrant? Which means you could have a second quadrant angle. How are you going to determine that? So let's take 180 degrees minus that 72.21. And you should get an approximate answer for a second B, possibly. So 180 minus 72.21 gives you approximately 107.79 degrees. Alright, so we have identified a possible second angle. Well, let's add 58 to that, because we don't want to exceed 180 with adding the 58, and we don't. We get approximately 165.79 degrees. So actually, this is a two-triangle solution. there will actually be two triangles in this case, because angle B and 58 get nowhere near 180, doesn't let alone exceed it. And then if you take that 72.21 away from 180 to get your second quadrant angle, you take that 107.79, add that to 58, you still don't exceed 180. So that's how you have two possible angles. So we'll call the first angle B sub 1 72.21 degrees. We'll call angle B sub 2 approximately equal to 107.79 degrees. So there's your two possible values of angle B. Now, that means since we have two possible values of angle B, we're going to have two possible values of angle C also. So let's solve for, let's see, the measure of angle C1 is going to equal that 180 degrees minus that 58 degrees, then minus that angle B1, so that'd be minus 72.21 degrees. So what does that mean? That means that angle C1 will have an approximate measure of, let's find the result of that. So 180 minus 58 minus 72.21, so angle C1 would be approximately 49.79 degrees. So there's your first possible angle C answer. Now we need to find angle C2. So to find that, you'll take the measure of angle C2, set that equal to 180 degrees, still minus that 58 degrees, but this time we're going to subtract the measure of angle B2, so that'll be minus 107.79 degrees, which now we should be able to get a 2 decimal place approximation for the second C angle. So 180 minus 58 minus 107.79 gives you a measure of approximately 14.21 degrees for angle C2. So there's your two possible measures of angle C depending upon what you got for angle B. Now if we have two possible measures of angle C, that means we have two possible lengths for side C also. So the plot thickens. We know sides A and B. We don't know side C. We have two values for C, so for angle C. So let's set this up to find side C1. Well, we know that, let's relate these to angle A and side A, because A has an exact angle. So that means we can take that 11.4 all over that sine of 58 degrees, set that equal to, now we want to find side C1, the first possibility for side C, all over your sine of angle C1, so that would be over the sine of 49.79 degrees. So that means that C1 would equal, C1 times the sine of 58 would end up equaling 11.4 times the sine of 49.79 degrees. And then let's see, that means C1 equals exactly 11.4 times the sine of 49.79 degrees. all over the sine of 58 degrees, which now we should be able to get a 2 decimal place approximation for the first possibility for side C. Alright, so we have 11.4 times, 11.4 times the sine of 49.79. Take all that, divide it by the sine of 58 degrees. To 2 decimal places, you get a length of approximately 10.27. So the first possibility for side C is approximately a length of 10.27, but we still have to consider the second possibility. So set up your sine of A to side A, so that side A is 11.4 over the sine of 58 degrees. But this time we want to find the second possibility for side C, so that would be C2 over the sine of your second angle C, which would be over the sine of 14.21 degrees. So then that means that C2 times the sine of 58 degrees is equal to 11.4 times the sine of 14.21 degrees. So then, I know I'm running out of room, but that means side C2 equals exactly 11.4 times the sine of 14.21 degrees divided by the sine of 58 degrees. And now we should be able to pull off a 2 decimal place approximation. Alright, so 11.4 times the sine of 14.21. Take all that, divide it by the sine of 58, you get a length of approximately 3.3. So the second possibility for side C is a length of 3.3. So sometimes when you have 2 triangle possibilities, you're basically going to do double the work for one problem. But the big takeaway is when you go to solve for that first angle, make sure that the second quadrant angle is also possible. And if it's not, you would only have 1 triangle. But if it is, then you have 2 triangles. And also, even if you just get, even on your first angle, you need to make sure the first angle plus the angle you already have doesn't exceed 180, because that would end up as a no triangle case. So watch out for that too. Alright. I'd like to at least find one where we have just a 1 triangle case. I'd like to show you them all for the SSA. Bonus points if we have another 2 triangle case. Alright, we're still doing a side-side angle triangle. That's a given, but what's the nature of this one? It's just going to be a wait and see till we get there. Alright. So, alright, angle A is 76 degrees. Side A has a length of 34. And then side B has a length of 21. Alright, so we have 2 sides and a non-included angle, so this is yet another side-side angle case. Now the question is, 1 triangle, 2 triangles, or no triangle? Well, we know both angle A and side A. We only know side B, so that means we should definitely go for angle B first. So we can take that length of 34, which is side A, divide that by the sine of 76 degrees, set that equal to your length of side B, which is 21, divide that by the sine of angle B, which we don't know just yet. So that means 34 times the sine of B equals 21 times the sine of 76 degrees. So then the sine of angle B equals 21 times the sine of 76 degrees divided by 34. Now let's see what we get here. Let's see what possible angle we could get. 21 sine of 76, divide all that by 34, so we get about 0.6, so yeah, that's within the domain. So for an angle, you get approximately 36.82 degrees. Alright, well, you take that 36.82 itself, add that to 76. You're not even close to 180, let alone going over. So we know we for sure have one triangle. But do we have a second triangle? How are we going to determine that? So take 180 degrees minus that 36.82. See what we approximately get here. I can pretty much guarantee we're not going to, that's pretty much not going to work. 180 minus 36.82, that would give you an angle of approximately 143.18 degrees. Well, 143.18 plus 76 would put you well over 180. That'd put you well over 200 degrees. So that's second possible angle definitely doesn't work. So that means angle B only equals 36.82 degrees. So that means we have only one triangle that's possible. Okay. So we know we have only one triangle. That means there's only one possibility then for angle C. So that means then that the measure of angle C is going to equal 180 degrees minus that 76 degrees minus that angle B, which is 36.82 degrees. So that means that C, we should be able to get an approximation for that. So 180 minus 76 minus 36.82 gives you that angle C is approximately equal to 67.18 degrees. Alright, so now we've solved for all the angles. The only thing that's left to do then is solve for side C. And since we have only one possibility for angle C, we have only one possibility for side C. So we have an exact length on side A and an exact angle for angle A, so why don't we relate C to angle A? So we can take that 34 divided by the sine of 76, set that equal to side C, which we don't know yet, divided by the sine of angle C, which would be 67.18 degrees. So that means C times the sine of 76 degrees is equal to 34 times the sine of 67.18 degrees. So C equals approximately 34 times the sine of 67.18 degrees, which now we should be able to get a 2 decimal place approximation. So 34 times, let's see, nope. 34 times the sine of 67.18 would give you a length of about 31.34. So that means the 2 decimal places, side C has a length of approximately 31.34. And I think we'll call it for this lesson. Next lesson, we're going to use the sine function to solve for the area of oblique triangles. So yes, there is a way you can use trigonometry to solve for the area of oblique triangles, and we're going to actually do that involving the sine function in the next lesson. So I hope everyone has a great day. Take care.